Right, chaps. So now we're gonna learn how to integrate. Um, well, I'm actually not gonna say what we're gonna do because it's a little surprise. So let me start with a question. Okay, if I gave you, asked you to integrate x cubed, okay, dx. Okay, I'm sure that not problem. You will straight away tell me it's x to the power 4 divided by 4 to get rid of that 4 that comes out plus c. Okay? If I ask you to integrate x squared, then you will tell me, okay, that's x cubed divided by 3 plus a c. If I ask you to integrate 1 over x cubed, okay, dx, then you'll say, okay, I'll first change it into x power minus 3 dx, and then I'll think, okay, that's x to the power minus 2 divided by minus 2, so minus half, okay, plus c, right? So then when we come to differentiate it, the minus 2 jumps up, cancel the minus 2, and it's x to the power minus 3. So it goes upward. As always, it always goes up. X cubed becomes x power 4. X squared becomes x cubed. X to the power minus 3 becomes x to the power minus 2. So if I ask you to do dx x squared, okay, in other words, x to the power minus 2 dx, then again you will tell me, okay, that's just simply x minus x to the power minus 1 plus c, right? You're just moving minus 2, we're moving up, okay? So that's all good. But now if I ask you, hoping I've got some space here, yeah. If I ask you to find what is 1 over x dx, okay? What will be that? The answer to this. I wish actually anyone was here because I would love to know really if you can figure it out, right? Now, okay, we're going to write it as simply x minus 1 dx. But now, according to these rules, I'm always going up, right? Minus 3 became minus 2. Minus 2 becomes minus 1. So you want to say, okay, so that must be x to the power 0 plus a c. In other words, well, what is x power 0? It's 1. But 1 plus c is just a c. It's just a constant. You know what I mean? It's just a number. But if that number, is that number just a constant? It can't be right. Why can't it be right? Because if the integral of this is that means that the derivative of this constant with respect to x must be x to the power minus 1. And we know that's nonsense. Okay, right? I mean, let me just make sure you understand that. If the integral of a function is a certain another function, then if I do the derivative of this function, I must get back this function. But we know that the derivative of any constant is simply 0. So it can't be that. So that can't be the integral. Okay? So we're a little bit stuck. We don't know what the integral, and let's write it now. What is the integral of 1 over x? Now to answer that, I need to remind you what we already know. Okay, maybe a second before that. If I don't know what it is, let's say we call it a certain function. It's a certain function that I don't know what it is. Okay? We will find out what it is in a second, but for now I'm just going to say that the integral of that is a certain function. Now, what is the fundamental law of calculus I've been saying quite a lot lately? It tells you. If an integral of a function is another function, then the derivative of this function must be what's inside the integral. Okay? So that function that I'm looking for, I don't know what it is, but I know that its derivative is 1 over x. Okay? So a certain function, I don't know what it is, if I find the derivative of that, okay, I must get 1 over x. Now I'm just going to check out something. Well, I can tell you now already, if you look back, you page through, I think in somewhere towards the end of term 1, we learned about a function that its derivative is 1 over x. And that function was the natural logarithm of x. Okay? Which you can also write down as log x base e. Okay? It's just ln x. Alright? So we've got the answer. The main answer here, the integral 1 over x is log x, the natural logarithm of x. I'll just pause here for a second. Okay, so if you look at the textbook, they will have this formula, but they will add one more thing to it, and I must add it. It is something that I need to add, and I need to put these two lines here. These lines, remember, it's the absolute value. Okay. So when I ask to calculate the integral of 1 over x, I really must do the logarithm of absolute value of x, and I need to explain why that is. What does the logarithm of x look like? The logarithm, the function y equals log of x, not without the absolute value. Okay, that function looks like this, right? It blows down to minus infinity, and it goes eventually slowly to infinity, and it crosses here at somewhere. Where does it cross? I guess at 1. I think so. Yeah, it crosses at 1. Okay. But one thing about this function, now I'm sure you know, and you can clearly see, it's defined only for positive x. It's not defined for negative x. There's nothing on this side. This is a vertical asymptote. Again, never crosses the y-axis. So it's not defined for negative x. Now, if I don't put that, okay, then I can put a minus value here. If I put a minus x, if x is negative, then I'm in trouble. Okay, I can't put the negative here. So I must always use the positive value. Okay. Now, I can go deeper into explaining why can I just do that, and actually there is some explanation in page 86, and you can look at it, but it's not really essential. So for once I thought maybe let's just keep it simple. You just basically need to remember that this is the case. Okay, so now let's move on to some examples. Okay, maybe one last thing before I go into the examples. I mean, when we introduced this log x, it was, if you remember, it's a bit random. Where's that log x from? Okay, and that's not the reason why I introduced it, but still, I think it's quite a good thing, because if we didn't have this log x, we wouldn't be able to integrate 1 over x. We can integrate x squared and x cubed and its power 4. We can integrate 1 over x squared, 1 over x cubed, but 1 over x, as I showed you just a couple of minutes ago, we wouldn't be able to integrate unless we made up that function log x. So that's quite cool. Right, so our first example is 1 over 4x dx. Okay? Now, what I suggest doing here, and I don't think I've done it before, that 4 is doing really nothing to me. It's just a constant. So a constant, I can always chuck out of the integral, of the integral sign. It's just a constant. So it can come out. I can write it as 1 over 4, the integral of 1x dx. Okay? It doesn't have any derivative. It's a constant function, so it can come out. Now that, I know what that is. This whole lesson is about that. So it's 1 over 4 ln absolute value of x. Okay, let's pause and I'll add some more examples. Okay, a couple more examples, a little bit more tricky. So now I've got 1 over 2x minus 9. I can't just, like here, just take out constant and then just have 1 over 2x. So again, I need to guess a solution. Okay, so look at this. The first one will be a guess that you might not have guessed, but then you will get it. So my guess is, okay, that is ln 2x minus 9. Okay. Now let me try and justify why is that a good guess. So if, again, and I'm saying it so many times, the integral of this function is this function, that means if I do the derivative of this function, I must get what's inside the integral. So let's try and differentiate 2x minus 9. If I do that derivative of that. Well, the derivative of that, this again, using the chain rule, okay, is ln of something, that's the outer function, and the inner function is 2x minus 9. So the answer will be 1 over 2x minus 9, okay, 1 over whatever here, times the derivative of the inner function. What's the derivative of 2x minus 9? Well, it's just 2, isn't it? Okay. So you can see why I had a good guess here, all right? Whatever is there at the bottom, and if it's power 1, the answer, the solution will be log of that thing. but we have a problem. This is time 2 and I only have time 1. So obviously I need to divide by 2. If I divide this by 2, okay, then if I do derivative of that, I'm going to get 1 over 2x minus 9 times 2, but that 2 is waiting for it, and voila, we got it. Obviously I'm going to add plus c. Okay? So hopefully now we don't need to do it again. Let's have a look at this example. What will be the solution here, right? You know, when do I use this logarithm really? I always use this logarithm when I have some kind of x in the denominator which has a power of 1. Okay, you can see the x is power 1. Obviously if I had, just to write something, if I had 1 over x squared and I do the derivative of that, okay, then I don't need logarithm. You know, that's just going to be x to the power minus 1 minus, okay, plus c. But when I have x to the power 1 with some constants and three numbers, then I must use the logarithm. So my guess is that it's 3x minus 2, log of 3x minus 2, right? If I do the derivative of that, I'm going to get 1 over 3x minus 2, which is great. But 3 is going to jump up. Okay? Now, do I want to divide by 3? No, actually, I don't want to divide by 3 because actually I don't want to have 1 here. I don't even want to have 3. I want to have 6 here. So really what I want to have is put another 2 there. Check this out. Okay, I'm going to put that 2 there. Okay? Why? Because when I do the derivative of that, the 2 is going to stay there. It's just a constant. The 3x minus 2 will move to the bottom, and 3 will jump out. 3 times 2 is 6. Okay? Right, I can do it. I did it quick. But if we want to do it slow, we can say, okay, I'm going to have the 6 there because I want to end up with a 6. And then I got to divide by 3. So when the 3 jumps out, it will be cancelled by that one. But what is 6 divided by 3? Is 2. So you can do it in either the slow way or the fast way. It doesn't matter as long as you know what you're doing. Okay, obviously plus AC. Great, let's move on to some nasty combination of logarithm with trig. Well, not nasty, but nice stuff. Okay, so now we're going to see how logarithms can help us find integrals of trig function. Now we've done integral of trig function, but if you look at what we've done last lesson, there would be nowhere we could just find this integral of these simple trig function like cotan and tan. I mean, I don't have the table here, but you don't have tan or cotan on this side that we can find it, and there's no substitute thing, anything you can do, some kind of identity that can help you. You can't solve it without logarithm. And I must say that this is actually quite tough. I mean, you'll see it now, you'll understand it, but because we know that we need to use logs. But if you didn't know that we need to use logs, as is the case in a test, you know, you don't know, they don't tell you you must use logs, I would also be very possibly stuck. Okay, so we're going to write cot as cosine divided by sine. Okay, now at this point you think about, hang on, this cosine is simply the derivative of the sine. So what if, it is a big if, you need to have serious kind of intuition there. What if I say, okay, let's suggest a solution like this, ln sine x, okay? Now, I'll be honest with you, I can't remember if I probably in the all these last example, one thing I really didn't do is put the absolute values. I must put the absolute values. So apologies, guys, for all these questions that I've had before, like, all these questions I had, I must really have put the absolute values. I'm just going to check out a second. Yeah, so just like solutions that I've done now, like just give you one integral. I think we've done that one, 2x minus 9 dx. Okay, the solution, of course, is ln 2x minus 9, but we need to put absolute values. So please correct that in your notes, okay? Right. So let's have a look at the solution that I suggested, okay? I looked at the denominator, sine x, and I said, okay, what about if I have the solution is like ln sine x? Let's do the derivative of that. Let's just write that. The derivative of ln sine x, okay? If I do the derivative of that, I'm going to get 1 divided by sine x. It just pushes it down, okay? Whatever is inside the ln get pushed down, okay? But then I need to time it by the derivative of sine, which is cosine x. And you can see we're getting that. So that solution, it was a good guess. Okay, all right, right, and obviously plus c. Next thing, let's look at tan. Tan is kind of, it's the inverse of cot. Okay, it's sine over cosine. So I'm looking for the integral of sine divided by cosine dx. Now you can think about, right, if here I had ln sine x, push the sine down, and here we have a derivative. It's a bit similar here because we've got cosine at the bottom, and sine is not the derivative of cosine, it's the derivative of minus cosine. So what I can do is, I can suggest something like this, ln cosine x, okay, ln cosine x, and then put that obviously in absolute values because I'm looking only for the positive numbers here. But if in my head, if I'm doing the derivative of cosine x, I'm going to get minus sine x, not sine x. So I must have a minus sign here. Okay? So as I do the derivative of that, the cosine gets shoved in the denominator, and then at the top I'm going to have the derivative of cosine, which is minus sine. Voila, minus sine times minus will give us positive sine. And obviously plus c. Okay, just check that I've got the right answer. Minus ln cosine x. Great. Now this one looks really ugly, but if you got those two, it's actually really easy. So I'm hoping, as I told you before, integration is all about intuition, and that's what makes it hard. Okay, because there's no like strict rules. It's kind of like a puzzle. So in this case, okay, there's no way you can separate in two fractions. I don't think so anyway. There's no identities that you can use. There's not squares. They're not timing each other. But let's just have a look at this. Look at the denominator. Let's do the derivative of the denominator. Let's do it in our head. The derivative of sine plus cosine. Well, the derivative of sine is cosine. The derivative of cosine is minus sine. So the derivative of the denominator is simply the numerator. So we can suggest something like this. Ln sine x plus cosine x, putting in absolute value before I forget that. And then let's just check that. The derivative of that, well, ln of something, that's going to push the denominator, time the derivative of this. But what is the derivative of some function? Is the sum of derivative of each function. So it's the derivative of sine, which is cosine, plus the derivative of cosine, which is minus sine. So voila, we got the answer. Obviously, we need to add a c. Okay? One more example. Last one. Okay, so here's another one, function that we can use logarithm to integrate. And again, it's one of those that is not very straightforward. And if, because we're using logarithm in this lesson, then we know we are going to use it. But if it was some kind of question in the test, I think I would also be stuck with it. Okay? So what's the clue here that we can use a logarithm? You basically look at the denominator and numerator, and you can see, again, just like with the one we had with the trig, the derivative of the denominator is exactly the numerator. Okay, let's just see that. So the derivative of e to the power x plus e to the power minus x, that's the denominator. If I do the derivative of that, it's going to be e to the power x minus e to the power minus x. Right, e to the power minus x is e to the power minus x times minus 1. But that is exactly the numerator. So at this point you think, okay, so I'm just going to put a ln e to the power x plus e to the power minus x, put the absolute value before I forget. And if I do the derivative of that, that's going to shove it to the denominator time the derivative of the top, which is simply the derivative of this, which is that. Okay? So that works. I think I'm going to end up this session with a similar formula that I gave you for the exponent. So if the integral of 1 over x dx is ln x, if I have an equivalent function, 1 over f of x, if I have a function, instead of just x, a function of x, and here by miraculous chance I have the derivative of that function, okay, dx, then the answer will be ln f of x, absolute value plus c. Okay? This is really it. So when would we use times you might use logarithm if you have a function in the denominator and at the numerator you have exactly the derivative of that function, then the answer will simply be the logarithm of that function that was in the denominator. Hopefully that makes sense. Have a lovely day.